This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. I'm your host Gavin Henry, and today my guest is Jens Gustedt. Jens is a senior scientist at the French National Institute of Computer Science and Control. He's the former co-editor of the ISO C standard and author of the Modern C book. Jens, welcome to Software Engineering Radio.
Hello.
Is there anything I missed in your bio that you'd like to add? I did keep it a bit short because I know you've been doing this a long time.
No, that's okay. That's okay. I have a much longer history for sure. But
excellent. I'll put some more detail in the show notes, don't worry. Okay, so during the show, we'll be talking about C programming history, legacy C, and then the last part of the show talking about modern C. However, I'd like to start with an overview of where C came from and how and why it became standardized. So what is C?
C is one of the probably oldest but still most used programming languages in history. So it started in the 70s, last century, long time ago, and was much related to the creation of what's nowadays the POSIX operating system. But it relatively fast became independent of all of that. So the essence at the time was to have a programming language, a higher level programming language, to abstract from machine-specific things, so people could program in a relatively abstract way things that are still relatively close to the machine. So this is where C comes from, at least originally.
And where was it actually created?
It was created in the Bell Labs, I think. So this is all related with, at that time, AT&T and Bell Labs, where they had this research group focusing on operating systems and these kind of languages. So there were precursory language, was a precursory language which is called B, or was called B, for example, and people trying to basically bootstrap what we nowadays know as computer science in a certain sense.
Would you class it as a simple language?
I think so. At least it's probably the simplest language of the major languages which are still around. So it's much simpler than C++, it's much simpler than Java or Python, or in a sense, or at least it has much less features than all these other languages.
And does it come with its own, you mentioned Python, that comes with its own interpreter. Does C come with an interpreter or compiler? Or?
C is a compiled language. So it doesn't come with an interpreter. It's compiled once and then executed, usually multiple times.
And where would you typically see it used?
You see it used in very different kinds of programs and environments. One major environment where it's still used is operating systems. So many operating systems today are still written in C, and the interfaces to the system are formulated with C functions and things like that. So most prominently Linux, the whole Linux system is written in C with very, very little assembly language underneath, and many other systems are like that. So this is one of the really big usages of C nowadays, still is everything which has to do with system and low-level programming.
I did a show with Howard Chu on the Lightning Memory Map database, show 371 for listeners that haven't heard of it. And he picked C because it's the lowest level language that he could do for speed and simplicity as well.
There is another related field, which is embedded programming, where you have these tiny little ships that you have nowadays everywhere around in your fridge or wherever. These tiny little chips which only have, I don't know, 64 bytes of memory or something like that, which just switch on your lamp, your bulb, or things like that. So there's really a lot of these processors now out there, and basically they are all programmed in C.
So you already touched that it's very popular. So I guess if it's in these types of devices and operating systems, that's as popular as you can get.
Yeah. Then there is an usage which is a little bit orthogonal to that, which is high performance programming. So which is, from a first point of view, really quite different from that. But there C is used because it's relatively simple, because it's relatively good understood, and because the compilers nowadays are really good in optimizing. So you're using C and then expressing your algorithm in a certain way. Your compiler can really well understand what's going on, what's that about, and how to improve this with all these optimization techniques that are around nowadays. Doing vectorization, doing all kinds of constant propagation and whatever they have invented.
So you've touched upon compilers. That brings me on to what the sort of ecosystem is around C as a compiled language. I'm talking about things like the GNU GCC compiler, Intel, Clang, the main ones. Is there a mature, stable, easy-to-use ecosystem around C?
Yes, I think so. So there are these public domain compilers that you mentioned, so GNU-C and Clang. They're basically functional for every processor, CPU that is around that you can imagine. So this is really an advantage of C also, that it runs on all kinds of processors everywhere. Then there are a lot of small compilers out there for all these tiny little chips, which cost maybe not a penny each or something like that. There are a lot of compilers out there that service these kind of things. So there's a lot of compiler infrastructure there. Now, the rest, let's say everything else, what you need to program C is an editor, is a runtime system, and things like that. So these are not, there's not one system out there to deal with your C or something like that. Everybody has their own editor, everybody has their own loader, runtime, and whatever.
And in relation to standards, what is a standard in the relation to a programming language? Sorry, I've used that word twice, but
yeah. For at least for me, it's important to have a standard for a programming language, because a programming language is several things basically. It's, for one thing, it's a way to express your idea of an algorithm and what you want to do, but it's also a way to talk to a machine, to the machines that you want to execute your code. And the important thing here is to be portable. And if you want to be portable, you have to say, how will this program behave independently on whichever CPU or machine this will run? And this is what the standard tells us. The standard says, if you do I+1, for example, then you will have the value which is incremented by 1, or whatever things are written down in the standard, how the arithmetic works, how basic functions work, how you interact with the I/O system, and a lot of things like that. So the standard tells us how these things are supposed to work and how a program is supposed to interact with its environment. This had been done for C the first time in '89. So this was the original ANSI standard C from '89, which was then taken over by ISO, the International Standards Organization. And then there have been revisions of that standard, the most important ones in '99 and in 2011. And now we had let's call it a bug fix release or something, which didn't bring much new features in 2018.
So is the standard, you mentioned, the standard is there for the processors, creators, manufacturers, but also the programmer and the compilers?
The standard is there for everybody. It's actually the contract that the programmer has with the platform providers or compiler providers. So it tells, if you give me a program which is constructed in such and such way, I, as a compiler provider, have to deal with it in that and that way and do these and these things then with that program. And the program has to behave in a certain way. So it's basically a contract.
And why was a standard created for the C programming language? What was the driving force behind it?
The driving force behind it was that when C was first developed, it was developed for a certain machine, which was called PDP 11 at the time. And then it turned out that these features this language had, everybody wanted that. And so they ported this language to their own processors, their own operating systems, etc. And by doing so, they extended the language. They had some other ideas. So everybody was doing things a little bit their own way. And if everybody does their things their own way, at a certain point, this is not portable anymore, because you can't take a program which was written for the PDP 11 and take it to another computer and so on. And so relatively quickly evolved an idea of nailing these things down and trying to fix things which were thought to be essential to certain things, and also leave some slack to the implementations to have possibilities for extensions in certain areas and etc., but to nail them down to a certain amount.
Yeah, because there's certain flags that you can have on the different public compilers that you mentioned that are only particular to that compiler, as I understand it.
Yeah, there's certain flags.
Is that what you mean by extensions?
There's certain flags, certain features that compilers allow. Then there's a lot of things that are, which in this C jargon is called implementation defined, that depend on the implementation of the compiler actually. For example, how many bits a normal integer has, or how floating point arithmetic is performed, and some things which are in a certain range to be defined by the implementation, and then the programmer can look up in the documentation or look into some macro values and things like that to know, when I'm on this particular platform, this will behave that and that way.
And is the process the same as it originally was, or has it changed to standardize a language? I guess you mentioned that there's little increments now, but I guess there was a lot of work at the beginning.
There's a lot of work in the beginning. There's still a lot of work, because the world is changing. So the language also has to change and to adapt. The process has, I think, not much change. I wasn't there in the beginning, so I can't tell you exactly how that was done in the beginning. In the beginning, there was this book by Kernighan and Ritchie, which basically described C, so which were the first creators of the first versions of C, and they took that into a standard, and they formulated and things like that. Then you have these. Now it's an ISO standard, so then you have these ISO procedures on how to create standards, and there's a whole section of ISO for programming languages. So C is not the only one which is normalized by ISO. There's also C++ and Fortran and COBOL and I don't know what. And there are certain procedures in place, what you have to do and how you have to do that. So this is an international standards organization, meaning that this is mainly driven by the member states of ISO, which were basically all countries in the world. And all progress has to be agreed upon by these national bodies that participate in this particular standardization of that programming language. So,
and I think you've already mentioned why it's really important to use a standard-based language, which
it is important to use a standard-based language to have portability, basically, and to ensure, in particular, forward portability. It's so that when in 10 years you will buy a computer and you will run your program of your company which does certain things, this program is still supposed to run on that machine, recompiled and things like that, but then still to run there.
And what enforces the standard when you're writing code? Is it at compile time that throws errors, or your tool set helps you, or the programmer?
Yes, this is basically for C at least. It is usually basically the compiler, or the compiler does the first scan, let's say, which is supposed for certain things to tell you, no, this part here is wrong, this is not okay, I won't accept that, and so I won't compile your program, which this is called in our jargon a constraint violation. So you have formulated constraints. For example, you should not add two integers which are too large, so that the sum will not be able to fit into the machine word for one integer. Things like that are formulated, and when the compiler sees construct like that, then it will tell you, no, here you have an error, and you will have to correct that.
Where can a programmer get the standard from if they're interested?
They can get it from ISO directly, from the International Standards Organization, which is relatively extensive to get. I don't know, something like $100 perhaps, or something like that.
Yeah, I'd wondered why it's so much, but if it's
but then you can also get it usually through your national body, which is, for example, for France, is AFNOR, so the French Normalization Institution, or DIN in Germany, or ICITS in the States, I think. And usually then it's already a little bit cheaper. And then you can look around and look for preliminary copies, let's say, of these standards, and you usually find a copy of these things, which you get for free somewhere.
Yeah, I think I bought the 2011 version for $40 or something, the draft one. I'll put a link into the show notes, because there's a nice page that tells you where you can get them from on the ISO89c.org or something. I'll put that in. Okay, I'm going to move us along to the next section, which I've called Legacy C. So now that we've covered what C is and how and why it came to be standardized, can we talk about Legacy C? So what do you mean, or what do I mean? We'll go with what you mean, because you know a million times more than me. What is Legacy C versus Modern C? And the ultimate question is, why did you write the book Modern C? That's where I'm heading to.
Yeah. So as I said, C is now something like 50 years old. And you can imagine that during the course of these 50 years, people came up with new ideas. Machines have changed, compilers have changed. And so the need is not exactly the same as it was 50 years ago. Then 50 years ago, the software engineering knowledge was not yet as present as today. And what I said about constraint violations, formulation of strong requirements for programs and things like that, they were not so much present in early C. So in an early C compiler would accept a lot of constructs which nowadays would not be accepted, and which would potentially have a lot of security issues, performance issues, or things like that. So the evolution of C has been to be a bit more strict on constructs, and by that catching errors much earlier, and especially at compile time, where old C or legacy C would not catch that at all at compile time, and then perhaps crash at runtime or something like that.
So do we think legacy C is a legacy compiler, or is there things in the C language? Can you give me some examples of what a legacy C program might look like, or functions from the standard library that no longer exist, for example?
There's only one function actually that has been deprecated, which was the getS function. But there are constructs which are now removed even from the standard. One example is the interface for functions. Functions in legacy C were defined by what's now called the Kernighan-Ritchie header, function header style, which was just giving a list of the parameter names of the function. And then after that, between this list and the function body, you had a declaration of the types of these parameters. But you did not have the type of the parameters in the declaration interface that you would see from other parts of your program. So basically, you would know perhaps that your function has 5 parameters, but you would not know that the first one is an integer, the second one a double, or whatever you have there. Or you have to look that up, and you have to know that the programmer has to know that, but the compiler wouldn't know it.
Yeah, that sounds more like an interpreted language, doesn't it?
It was not interpreted. It was compiled to something wrong if you did it wrong. So since C99, there are function prototypes. So if you use these function prototypes, you have the type and the name, and everything is checked at compile time normally and things like that.
Yeah, that's what I mean. I mean, if you're using, for example, interpreted language, you need to go and look up the API and check you're passing in the right parameters. But on the KNR, you said you couldn't do that before. The compiler would just take whatever.
Yeah, the compiler would just take whatever. It has some standard how to process these arguments and how to put them on the stack for the calling function, etc. And if the calling function interprets them differently, your program would just do random things and crash and publish your credit card number or whatever.
That would be in the hacker cracker terms.
Yeah,
that'd be Stack Overflow or a heap.
Yeah, for example, you could have Stack Overflow or any kind of misbehavior.
Do you think that's still as common as it used to always be? If the compilers are much better now, I guess that's a smaller surface of attack, is it?
The attack surface is certainly smaller. It's C is still quite permissive. So if you do what C calls cast, so casting away the type of a variable to something else, then you can still do a lot of harm. But to come back to what's legacy C and what's modern C, so this is for what I meant this calling convention for functions was something where there was a new thing introduced in C99, which was prototypes. And the old convention was still kept until last autumn. So we just removed these Koenig and Ritchie calling conventions from C just half a year ago or something.
So that's from the standard, but that might not be implemented in the compilers.
That's from the standard point of view. From the compilers, they all had to implement it still because it was still in the standard. But usually the compilers nowadays, if you are trying to use these interfaces, would tell you something. Do you really mean that? I think you should perhaps rewrite your function to be better or something like that. But so there's a whole line of progress from this legacy C to modern C with more interfaces that are more secure and also more efficient and things like that. So this is why I found it necessary at some point to write these things up and to emphasize on this fact that there are modern interfaces, modern things to do, better things to do with C than the legacy interfaces. Because this traditionally C is really long in deprecating things or even phasing things out. So things will work a long time if you use old interfaces, and you're not forced to use the new ones.
And this might be interfaces into the operating system libraries or the standard
interfaces into the operating system or means to program. So there are certain ways to program, for example, doing for numerical algorithms, doing matrices, passing matrices to the functions. There's a more modern way to do it where you can basically propagate the bounds of these matrices. But people don't use them because they learned perhaps, or their teachers learned C 30, 40 years ago where these things didn't exist. And so they still stuck into this more or less old world, deprecated world of ancient C, which then never progresses. So
maybe that's the title of this section, Ancient C instead of Legacy C.
Yeah.
But it's pretty impressive. There's only one standard library function that's gone in 50 years.
Yeah, that
doesn't need to be underemphasized, does it?
Yeah, it is. It is. If you look at other programming languages, they are much more pushy and deprecating things.
Oh, let's not talk about the JavaScript ecosystem. You can have a failing program within 2 months. It moves so quick.
Yeah. So this is
JavaScript's still good.
C people are a really conservative bunch. So they really hesitate to deprecate things, and the driving idea is really that I want to be able to run my program that I had 20 years ago and perhaps still in the next 10 years or something like that. Really having legacy in the sense of really having code that is known to work, that you can reuse that for a lot of years and really keep up your investment. Actually.
So it's a good ecosystem and skill set professionally and personally, or even hobbyists, to invest in, because it's not going to change too much as long as you keep on top of things.
Yeah, and it's relatively easy to keep on top of things. So it's not inventing something new every year or something like that. So.
And what tools? I mean, you touch on some of them in your book, but what tools are there to modernize your ancient or legacy C? Just a modern compiler, or?
Yeah, the most important thing is really a modern compiler, to have a modern compiler. And you have these public domain compilers, which are really good nowadays. So GCC and Clang really do a good job and have a lot of optimizations built in that work quite well. The C libraries also are quite well. So with C is not only programming language, it's also the C library, which interfaces to the operating system. And these are environments which are really stable, which are really high quality. And to that, in addition, you have also vendor-provided compilers and vendor-provided libraries for special architectures. For example, for high performance computing, you have these compilers from Intel, for example, which are even better in optimization for especially for Intel chipsets and things like that. So you really have high quality infrastructure for everything you want to do.
And just to finish off this section, with the compilers, when would you decide to go for a non-open source one to a vendor one? Does it just depend on the sector you're in or the type of program?
Probably it depends. So first of all, you have to be on an architecture where the public domain compilers work. So they probably don't work on every chipset. So if you are on some particular embedded processor or something like that, which is new, maybe GCC or Clang don't work, and you have to buy the compiler which comes with this chipset, which is provided by the chip manufacturer. Then you have these compilers which are really built for performance. So Intel is one of the examples. So you have Intel chips in many of these high performance computers nowadays, which have thousands, hundreds of thousands processors, and every cycle counts. And so you want to have something which really is capable of using this architecture as optimal as possible. And so then you would go for a vendor-based compiler that works with these things.
That moves us nicely on to the modern C,
Yes.
or modern compiler section, we could call it that. So just to summarize or mention again, what is modern C?
So modern C for me is the C as the standard defines it now, and not 50 years ago or 40 years ago or something like that.
And what modern C resources are out there for learning more about that standard or how to implement it, etc.?
There's my book.
Obviously.
For sure.
Big tick for that one. You just need to stop there. That's all you ever need in life.
Yeah, you get quite far with it. Otherwise, actually, there are a lot of books out there about C and a lot of platforms and things like that, with a special emphasis on modern C. Not so much less. And this was the main drive why I wrote this, because I saw that this was lagging behind in some sense. And then you have the standard. I don't know. I have a certain view on the standard, and I almost know it by heart. So probably it's a wrong person to ask. But for me, often it's just the easiest way is to look into the standard. And this construct, I want to know how this works, and then I look it up in the standard, or how this and this function has to be called, or what are the specialities of certain things, and then I can look it up. The main part of the C standard has 500 pages, so this is something you can master in a lifetime, compared to other languages where it's impossible. But
given so much is in the cloud, we're in 2020, is modern C fully compatible with continuous integration and continuous deployment environments? to get your code into the cloud?
Yes, I mean this certainly depends on the application. So C by itself, it's relatively raw. So if you need libraries to communicate between your different processes in your cloud, or have a database or whatever, you need things on top of C. So you need libraries and access to things and access to a file system and all that thing.
And is there an ecosystem around this? Like Python and Perl all have their different things. JavaScript has NPM. Is there a go-to sort of C module library place that you can look for recommended and popular things to bolt on?
I wouldn't know that too much.
Yeah, you're always waist deep in the standard, so you probably don't see that.
Yeah, I'm waist deep in the standard and programming really in C itself. So, and doing things like that. So
I do personally see when you go onto the various different source code repository tools online that when you're doing your testing file, so when you do a commit and it runs your test suite, it does have off-the-shelf templates for C, so it is obviously in the cloud like that.
yeah, it's probably, and all these platforms. So if you have Git or whatever, these are underneath. They are themselves implemented in C.
Yeah, Git and the Linux kernel is two of the most famous things written by Linus Torvalds, aren't they? So I think we've already covered. My next question was, where do you see most of the work that has gone into modernizing C? I think we've covered that with the standard.
Yeah, and the standard and the compilers. There's really a lot of work going into the compilers. So this is really the part that is really active, and there's still a lot of development in optimizing things better, and vectorization and threading and whatever.
And do you have any insight into the teams and the workforce behind the compilers and the standards? Is it an aging workforce, or is there always a new generation coming in?
I think the average age is half my age, something like that.
That's good. That'd be in well, for me that's in 20s.
for me that's a little bit more, but
yeah.
No, there are a lot of young people in there.
That's good.
And I mean, this is a relatively specialized thing. So if I see, so I'm also a scientist and have PhD students and have a group and things like that.
That's why you kept mentioning vectors and matrices and stuff. That's sort of in that field, isn't it?
Yeah. And I see that the PhD or former PhD students from our group, because they really have this relatively deep knowledge in compiler optimization and things like that they easily get jobs in these companies like Intel, Google, IBM, or whatever, because this expertise is really thought and needed for by these big players to optimize their compilers.
We've done a few shows on compiler design and how to create your own language. I've completely forgot to put them in this show outline, but I'll put them in the show notes after. I'd like to talk a little bit about some of the things I've seen in your book. So you talk about acquaintance, cognition, experience. Is that how you say it?
Yeah.
Can you briefly explain what these are and where these fit in a C programmer's career?
The idea of the book was to organize the book in levels. So having something like a basic level at the beginning and trying to get people acquainted with the basic things and how to write a program and keep things going. And then there are certain other levels on top which are more specialized, more complicated perhaps also, and where you really have to be a bit more experienced as a programmer to really appreciate them. So you can read through them, but if you don't practice, if you don't have the real problems at hand that for which you need them, this might not bring you so much, at least at that point. So the idea really is to have it constructed from the bottom to the top in a certain sense, and have, as far as I remember, I think 4 different levels of experience or for these things. And the last level really is one where probably people will see that in their whole career, every part of it at some point, but it's probably each of these points is perhaps only interesting when you are really confronted with that.
And would you get these different levels from just working in C, or would you recommend that someone reads around the topic and plays with other things to get ideas, or how does that work? That's just a normal career.
Usually in programming, still the careers are that people learn things by doing in many parts, and therefore I hope that such a book can be a good thing to put beneath somebody who's programming that, and giving the opportunity to reflect at a certain point on this and this point of view of doing things, or seeing how signals work or how threads work in C and things like that. Having something to relate to and look things up, perhaps after using them for a certain time, or being able to look things up. So probably such a thing will not be read completely linear from front to the end, but coming back to it several times in different parts of the career.
What modern things are there to make a C programmer's life easier? And that brings us on to what sort of tools do you see and personally recommend to make your programming life more fun?
More fun? Huh.
Not that it's not fun, but
There's certain things. I already mentioned these different kinds of matrices and things like that, function interfaces where you can put the bounds of your arrays and things into that. This is, for example, something which a lot of people don't use that could use them. There are other things where a lot of people have to program threads nowadays, so parallel programming in a certain sense. And if you program threads, you have to be careful that one thread doesn't erase what the other has written. So you have concurrency programs, races between your threads. And for many years, the basically only tool to protect you from that such things had been mutexes. So you would take a mutex in the beginning of a critical section, do the thing you want to do, and at the end relax the mutex, and then you're sure that during you have that mutex, no other thread can change the data on which you're working. This is it has a lot of performance issues and has also a lot of security issues, because you have to think of taking log and think of releasing log at the end and all these things. Since C11, we have a tool which is called atomics, where you can do, which are data types, on which you can do small little operations just like that. So you can have an atomic which represents an integer, and you can add up 1 to that integer, or 5, or whatever you want to add. And you're guaranteed that all of this is thread safe, and you're guaranteed that it uses the most efficient implementation by the compiler underneath. So you have this feature, which is just a simple, mostly a simple qualifier, which you put onto your integer. You say, my integer is to be atomic. And then afterwards, you're guaranteed that you can use it in a thread context and you won't have problems with that. So this is an example where things are really much simpler to use and more efficient at the same time, and which still is not used very much in the community, although it's there since C11.
No, I always understood it to be a mutex as well. Could you just give us a slight refresher on a thread in case anyone hasn't come across it? I doubt it, but...
Yeah, so threads are executions of the same program in parallel. So you can say in your program, I want to do this and I want to do that, and do these two things at the same time. Because you have multi-core processor, for example, with several cores, so your machine can do several things at the same time. So you have to have some way of telling it, I want these things done. I don't want them to be done one after another. I want them to be done in parallel.
So would a thread correspond to a CPU, a core?
Yeah, thread basically would correspond to a core. And these two cores then can do their thing. And when they're finished, they have to join somewhere at the end and then mix the results or whatever you're doing. So a typical example would be, and this is also something which is in the book, a typical example would be if you have a game, you would have one thread which is responsible for the graphics and drawing all these things. You would have one thread which is responsible for taking keystrokes, for example, from the user or your joystick or however you interact. And another thread which would do the accounting of how many points you have gained or whatever. All these things are basically independent. You don't want to, for the graphics to wait that you put in as keystroke, for example. You want these things to be to run in parallel, but they have to interact in some way. So they have to write messages in a certain way or have to tell each other, now there was a keystroke, so perhaps you should put a cross in that point here or whatever you're doing in your game.
Okay, I'd like to move us into some specific examples of what modern C looks like versus the things we see online in older books. Is memory management classed as a legacy construct? Do we still do this, and what does it look like now?
Memory management has not much changed yet. So basically, you still have the same functions as you had 40 years ago, which are malloc and free and some variants of that, to dynamically get memory. There is one aspect which is different from legacy C, is that you can have arbitrary large objects on your function stack. So you can declare a really big vector on your stack. But this has pitfalls. So this is perhaps not such a good example.
Okay. Could you give me 2 examples of what we shouldn't do anymore that you see all the time?
What we shouldn't do anymore?
Yeah.
Basically, the most important things that you should never do is casts. And people do that all the time. This is, they take a pointer to something, to double, often they do it between float and integers. They take a pointer to a float, which is floating point value. So the bits, to understand the floating point value, you really would have to understand the bits in a really sophisticated fashion. And then they cast this pointer to an integer, and then they manipulate this integer, and then they cast it back to float and hope that this is still a valid floating point, for example.
Why do they do that? Is it harder to do it properly?
Because they think that this is more efficient. Because they have learned in times 40 years ago or 30 years ago, or their teachers had learned that and have taught them that you have basically to be really efficient you have to do bit manipulations yourself, which is not true anymore. In the contrary, it's nowadays the compilers are much better of doing all these optimizations, and then you can do them by hand, and particularly they do them well, or they will do them well even in 10 years when your program runs on an architecture what you never dreamt of capacities it has.
So gone are the days where you shouldn't trust.
Yeah, you basically you should trust your compiler. Yeah.
I had another question here, which is what does modern C make easy? But I think you touched upon that with threads. That was a good example. Thank you. I love the takeaway section of your book, which is a brilliant cheat sheet because you can just go down the list and quickly find things. One I always like to see is item 7.6 for people that have got the book, which is the exit _ success and exit failure macros, where people normally put return 1 or 0. Can you think of 3 of these takeaways off the top of your head that would surprise a C programmer that learned C 10, 20 years ago? That they're looking down that and they go, oh my God, I've seen that in all of my code and they need to fix it. Sorry, I'm putting you on the spot.
Yeah, you're putting me on the spot. No, I don't.
Not a problem.
Sorry.
So what's the hardest part of a C program to write, do you think?
The hardest part?
Yeah, it's probably the same with any program, I would say. Just a black. I'm not sure.
I don't know. It's difficult to say. I mean, it's in C. Usually, it's relatively easy to start things. You start an idea, and then you get easily mired into something, and it gets bigger and bigger. But this is probably the same for every programming language. And then at some point, finding the cutoff point and get things shorter again and more concise and better to understand and things like that. So that's probably the most difficult part. One of the difficult parts of C itself, which is relatively specific, is, as I said, it's a permissive language. So it really only works well with self-discipline. So you can always C allows you to shoot yourself in the foot, no problem. The compiler has no problem with that. So you really should follow certain coding standards, certain rules to what not to do. As I said, casts, for example. If you disallow casts, your code is 100% more secure or something like that. You should always initialize your variables. There are a lot of things like that where you can have coding standards in your project, in your company, for yourself, which helps you to code well in C. If you don't do that, if you just write as it comes, write your code down as it comes, and just patch here and there, then you can probably get very, very bad code also.
Yeah, I think that's similar with a lot of programs, but
yeah,
C programs let you away with a lot. Is that one of the main reasons for the infamous security issues with C, or is that still so common now that the compilers are better?
There's still a lot of problems which for security in C, because one of the things that C does in many parts is what they call undefined behaviors. So there's things which are you're not allowed to do, but which are difficult to track, and so the compiler might not tell you that this was not a good idea. Which is, for example, if you don't initialize your variables, and C still allows you not to initialize your variables, and you forget that, and you pass, for example, pointer to a variable in a function somewhere deep down, and then all of a sudden somebody accesses this variable, and then the value there is some complete garbage, and then everything goes haywire. So this is still something which can occur.
It's a strictly typed language, though, isn't it?
It's a strictly typed language, yes, and that's strictly typed. So your variables are typed and strictly typed, but you have casts, so you can try to cheat. You can still tell the compiler, no, this I want to see this variable now as being such and such. And then you also have the difficulty that you have everything which is allocated. So malloc only gives you a pointer to void, so there is no type there. And you have to somehow put a type on such an object that you get by malloc.
Yeah, so that gives you some memory that you're free to allocate.
It gives you some, it gives you some memory, but you're completely free to put something in there with whatever type you like. And if there you get something wrong in one part of your code, you interpret it as one type, and in another part you interpret it as another type, because you dig around with pointers to this part or something, then you may be in real trouble. There's another part which is also quite dangerous, which is bounce checking. So C has no built-in bounce checking. And if you access vectors, you have somehow to cope to know how large this vector or matrix is. And if you're not careful and don't use the modern tools that you have by tracking these sizes of the vectors, then you can be in deep trouble, because then you access elements beyond the bounds.
What modern tools are you speaking about there?
What's called variable length arrays, where you put the size also in the size which you pass over to a function, and so the called function can know how large this array is. Does not only see a pointer, but it also sees somehow the length, and you can then query this size and act upon that size and be careful and things like that.
Okay. I understand you're working on in quotes, a common C++ core specification called N2494.
Yes.
Can you tell us what that is and why it is needed?
So C++ is a sister language or cousin or whatever, how you want to call that deviated from C a long time ago, but still had connections to C. So it's a language which is moving much faster, much more innovation there, but also much more errors and things like that. So they had to withdraw things that had added to the language, and etc. So in that sense, C and C++ are somewhat complementary, where C is really slowly moving forward and C is moving very fast, but sometimes 2 steps forward and 3 steps back or something like that. And they still have a lot of common syntax and a lot of programmers actually which do both. And there are features in C++ which stabilized years ago and which would be really good things to have in C. And on the other hand, for C++ in certain parts, it would be better to have more stabilization and more this compile type checked aspect that C also has. So there is this common intersection which would be interesting, which could be interesting, which is done by a lot of people. In certain sense, if you look on Stack Overflow, people often mix up C and C++ and don't really know the difference and things like that. So there's really some sort of intersection of a community. And the attempt I have started here is to formalize that intersection a little bit better and try to get to move the two communities to agree on something like this common intersection.
Excellent. That sounds really exciting. I'll make sure I get the links into that in the show.
Yeah. which is a kind of project to have. So I don't know if this will succeed or how far we will get with that. It's not only about programming and about specifying programs. This is also a lot of social interaction, people who are in their tribe in a certain sense, and which you have to move and to convince that perhaps these other guys, they also programmed them 30 or 40 years. They might have ideas which are not too bad, and so it will demand a lot of social skills also.
Yeah, I remember listening to a show on software engineering radio before I became a host, where it was about C++, and they were talking about the new features in the spec, similar to what we've touched on. And it did sound like there was a lot of similar things. Okay, I'm going to start to move to wrapping up the show. So obviously, C programming has a bright future, but if there was one thing a software engineer should remember from our show, what would you like that to be?
I would want them to look around, or to not to get too much stuck into their things, how their habits are to do things, but to be open to look around and how other people do it, and how modern ways to do things that perhaps you have done since 30 years or something like that. So really this opening aspect.
Are there some reference type of projects or repositories that you'd like people to look at, or that you go to look at some beautiful code that's simple and done right?
I particularly like the Musel C library project, which I was at some part a little bit involved.
Yeah, I think I've heard of that because of you.
Which was an independent C library project created by someone who was say disappointed by the glibc, which is the one which is basically most of the time used in Linux, because this was too much bloated and whatever, a lot of technical reasons. But what these guys have implemented there is really a nice thing of really small functions, readable code, really nicely done. For people who at least who are interested in systems programming and C, this is really a good reference code to look into how things can be done with a good coding standards and things like that. It was created for embedded devices, so this is a C library which is really small. Also, if you link it to your code, it's really can just links the functions you need and nothing else, and it's really small. So this is really a nice code space to look at.
Would you reach for that because you're in the embedded space versus glibc?
I'm not really in the embedded space. No.
No, I mean, as a programmer, is that why you would pick it, or just because you want to, versus glibc?
It's at least as efficient. It's much smaller, and one of the main goals is to implement a standard. So glibc has a lot of extensions, a lot of things here and there. But to really use it, you have to look into macros that are defined and which version and whatever, because it changes also too much. In Musel, you don't have any macro which tells you that you are in Musel, because they suppose that you are using the standard, and so you don't have to know which implementation of the C library you are.
And you spoke about having variables C strictly typed. Why does the compiler let you get away with not initializing that variable? Is that something you can tell the compiler to do?
Some of the compilers have actually option to say, initialize all variables.
Some type of default.
It's relatively new. I know of someone who just did that for Clang, if I remember correctly, and then looked into the performance issues that could come from that, because the idea is that they don't do that because they don't want you to initialize the variable when it will be changing right after anyhow and things like that. So not wasting any cycles.
I see.
But this is mainly obsolete nowadays because these compilers have such good flow analysis that they are able to detect when you never use a value, so they don't assign that value anyhow, and they only do the first real value that is used afterwards and things like that. So the performance decrease of something like that would be perhaps 2% or something like that measured. Depends on you.
Yeah, and if you're in a memory constrained environment, I suppose having loads of initialized variables would use up more memory.
No, it's more a question of processing time, I think. Depends, yeah. It depends on to which value you initialize some variables. So this can be a little bit more space also, yeah.
Oh, they would be compile time, wouldn't they? So it would be in the binary.
Yeah. So there are different aspects on that. This is compile time. This is space occupied at runtime. So but these are in the percentage ranges, and compared to the security gain that you get, I think for me that's a no-brainer because there's so many security issues because variables are not initialized and then have garbage values and programs crash. So for me, the security aspect would come first. I first want to have a semantically correct program, and then I want to think of how to optimize it. But not first optimize and then see if it does what I want to do.
That's a perfect explanation. Thank you. Was there anything we missed that you'd like to mention?
No, I think we have done a good tour, I guess.
Yeah, we could talk for hours on this, but I've only got 65, 70 minutes. So where can people find out more? You've got a Twitter account. How else can people reach out to you, get in touch?
I have a Twitter account. I have a blog, which is not so active in the last times, but still I sometimes publish things on my blog.
With everything going on at the moment, we've all been given more time, haven't we? I suppose.
Yeah, exactly. And then there is a web page for my book where you can find things.
Yeah, I've got that in the show notes.
And where you also can put in bug reports if you find a typo, or if you find I have some other questions, you can also ask them there.
And sorry, this is a bit of a personal question, but what's the reasoning behind the free book on your website?
For me, the reasoning is quite simple. I'm a public servant. I'm paid by the French state for doing the things I do. And I don't see any reason to get a top on my salary for the things I'm paid for doing.
Okay. Sorry, I just thought I'd throw that out there. I was just interested.
No, it's a good question. I'm also an editor of a scientific journal and things like that. So I had, in some sense, bad experiences with a lot of these scientific publishers, not the book publishers, but publishers of scientific work, where we as scientists do basically the whole work and write things up and write them in LaTeX and whatever. And then these guys publish these things, don't give us a dime, and make a lot of money on that.
So you've cut that straight out by making it free. Excellent.
Yeah.
Okay, Jens, thank you for coming on the show. It's been a real pleasure.
Yeah, it was nice.
This is Gavin Henry for Software Engineering Radio, and thank you for listening.
Bye.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.